Hello, let me take you through the Haber process. Haber process, you should know that it is the large-scale manufacture of ammonia. So Haber process is the industrial or large-scale manufacture of ammonia gas NH3. And when you hear of the Haber process, there are several things that you must know. So by the end of this lesson, you should be able to know the following. You should ask yourself, what do I need to know about the Haber process? So these are the things that you must know. Number one, the raw materials and their sources. So you should know which are the raw materials and where can you get them. So we only have two raw materials in the Haber process. We have nitrogen and hydrogen. You should know where to get each. The other thing you need to know about the Haber process is the impurities that are present in the raw materials and how to remove them. So you should again know that the impurities can impair or they can poison the catalyst. So you should know the reason why we are removing these impurities during the Haber process. The other thing is the reacting volumes. The reacting volumes are simply the mole ratios. The reacting volumes they are also going to be equal to the mole ratios. So you should know how many moles of nitrogen combined with how many moles of uh, hydrogen. Or in other words, you should know how many volumes of hydrogen combined with how many volumes of nitrogen during the process. The other thing you need to know is the catalyst that is used. So you know the name of the catalyst. Here we use ion catalyst. The other thing is you must know how to write the balanced chemical equation for the reaction that occurs, because this chemical reaction is the one that is going to give us the reacting volumes. The other thing, you should know that we need to produce maximum amount of ammonia using the reactants that we are going to use. So for maximum yield, we need optimum conditions, the best conditions, the best pressure, the best temperature, and the best catalyst that is needed there. So you must know all these conditions that are necessary during the process of this process we are calling Haber process, which is the manufacture of ammonia. The last thing that you need to know is the uses of the ammonia gas that we are preparing. So as you know that, then you know everything about the Haber process. It is that simple. Can we start with the raw materials? So the raw materials, we only have two raw materials in the Haber process. Just looking at the structure of the molecule NH3, we have nitrogen and hydrogen. So we only need nitrogen gas and hydrogen gas. Those are going to be our raw materials during this process. Now, we have said we need nitrogen, and the chemical formula for nitrogen gas is N2. Then hydrogen, its chemical formula there. So when you are told to give the name, you write the name in words. Do not write the chemical formula. But when you are told to write the chemical formula, do not write the word nitrogen. Just write the chemical formula. Those are the two raw materials. Now, can we see where to get them? So, nitrogen, if you look at the air is a mixture of gases, and the largest component of air is nitrogen gas. So, we can get nitrogen gas for the Haber process from the air. But the biggest question is, how can you obtain nitrogen from the air? It is only through this process, one process we call fractional distillation of liquid air. So nitrogen, you can obtain it from the air through fractional distillation. So the method is called fractional distillation of liquefied air. So how is this done? First, remove the solid uh, components of the air. In the air we have smoke particles and dust particles. Those are in solid state. So you first remove them through filtration. You pass it through filters, which you remove the particles. Then the second thing, during this fractional distillation of liquefied air, you you just remove the gaseous components of the air, which can easily turn into solids. Why should we remove them? Because once they solidify, they will block the pipes that connect the chambers. So to avoid blockage of these pipes, then we must remove carbon dioxide, which can easily turn into a solid when cooling, and also uh, water vapor. Water vapor can easily turn into, when you cool it to very low temperatures, you can go condensation and then freezing and become ice. So ice is a solid which can block pipes. So we have to remove it. So once you remove those, then you cool the remaining air into temperature of about negative 200 degrees Celsius. At that temperature, the air, all the components of the air are in liquid state. Then when you allow it to, when you allow the temperatures to rise slowly, then you are going to collect nitrogen. So nitrogen gas will distill at negative 196 degrees Celsius. So it will come out as the first fraction. So that is now the process of fractional distillation of liquid air. That is the source of nitrogen during Haber process. So the second raw material is hydrogen. So hydrogen, you can obtain it from two sources. The first one is cracking of long chain alkanes. Long chain alkanes are simply hydrocarbons which consist of many carbon atoms per molecule. Now, when you carry out the process of cracking, this process of cracking is simply breaking down these long chains into shorter chains. And in the process of cracking of long chain alkanes, we usually form three products. We have short chain or shorter molecules of alkanes. We also have alkenes and hydrogen gas, which is formed as a byproduct. So during cracking of long chain alkanes, hydrogen gas is formed as a byproduct, and this hydrogen gas, we need it in the Haber process. So that is a source of hydrogen gas, cracking of long chain alkanes. The second one is electrolysis of brine. So what is electrolysis of brine? Brine is a solution, or it's a concentrated sodium chloride solution. So electrolysis of this solution is simply passing an electric current through the solution. So when you do that, when you pass an electric current through concentrated sodium chloride solution, then at the anode, chlorine gas is formed, and at the cathode, hydrogen gas is evolved. So this hydrogen gas, which is formed at the cathode, we need it in Haber process. So electrolysis of brine is also another source of hydrogen gas. So in short, the sources the sources of the raw materials: nitrogen is fractional distillation of liquefied air. Hydrogen, you can get it from cracking of long chain alkanes, and electrolysis of brine. Once we have obtained these impurities, once we have obtained these raw materials, you should know that they contain impurities, and you are supposed to know here the names of the impurities that are present in these raw materials and how to remove them and why, the reason why we remove the impurities. So the impurities that are present in these raw materials include carbon dioxide. We also have sulfur dioxide and dust particles. So all these are impurities that are present in the raw material. So they must be removed before you react nitrogen gas and hydrogen gas to get ammonia. So why should you remove them? Remember, we are going to use a catalyst, and the catalyst can be easily poisoned by these impurities. So we remove impurities to avoid poisoning of the catalyst. And what is poisoning? This simply means reducing the efficiency of the catalyst. So poisoning of the catalyst means reducing its efficiency. And how, for example, for instance, how is this efficiency reduced? Catalysts will speed up the rate of it will speed up the rate of reaction. It will speed up the rate of production of ammonia by offering a site over which it will increase surface area over which the raw materials or the reactants will combine to form the product. So it offers a site over which these raw materials are going to combine to form the product. And once we have impurities like dust particles, they form on the, or they get deposited on the surface of the catalyst, then it cannot work efficiently, and that is the reason we have to remove it. So that is what we call the poisoning of the catalyst. And the other question you should ask yourself in this Haber process is, how do these reactants combine to form the product? So how does nitrogen gas combine with ammonia, with hydrogen gas to form ammonia? So it is so simple. You have to write a balanced chemical equation for the reaction. So nitrogen gas reacts with hydrogen gas to form ammonia. Then when you balance, you will see that 1 mole of nitrogen gas combines with 3 moles of hydrogen gas to form 2 moles of ammonia gas. So when you get these mole ratios, for example, you can see 1 mole of nitrogen is combining with 3 moles of hydrogen to form 2 moles of ammonia. That mole ratio, will be the same as the reacting volumes. So this means 1 volume of nitrogen will combine with 3 volumes of hydrogen to form 2 moles of ammonia. What does this mean? If you take, for instance, 1 liter of nitrogen gas and react it with the hydrogen, so it will react with exactly 3 liters of hydrogen gas, and it will form only 2 liters of ammonia. If you use milliliters, 1 milliliter of nitrogen will combine with 3 milliliters of hydrogen to form 2 milliliters of ammonia. Now, these reacting volumes, they translate to the mole ratios. So another example is when you take 1 mole of nitrogen, it will react with 3 moles of hydrogen to form 2 moles of ammonia. So those are the reacting volumes, the amount of nitrogen that is required to react completely with the hydrogen gas. So when you have 1 mole of nitrogen, you need 3 moles of hydrogen gas, and it will give you 2 moles of ammonia. Now, Let me give you the summary of the Haber process, and I will do it in form of a flowchart. So from the chemical reaction, we have seen that 1 volume of nitrogen combines with 3 volumes of hydrogen gas, and these are the raw materials. So the raw materials, the starting materials in this process, it is nitrogen and hydrogen. We need 1 volume of nitrogen and 3 volumes of hydrogen. So remember, these are the raw materials, they contain impurities. So what do? We first remove the impurities by passing this gaseous mixture through a purifier. So the purifier will remove sulfur dioxide, carbon dioxide, and dust particles, which are the impurities. Why should we remove them at this stage? Because they can easily poison the catalyst. So we remove the impurities. The purifier will remove impurities that could otherwise poison the catalyst. After purifying, the pure now mixture will be taken to a compressor. At the compressor, the pressure of this mixture will be increased to 500 atmospheres. And why should it be put at 500 atmospheres? Yet in Haber process, we only need a pressure of 200 atmosphere. This is because when you pass this mixture from the compressor to another chamber, then the pressure is going to reduce. Because when you look at this now, from the compressor, we take this mixture to another chamber where it will be heated. So in that chamber, the pressure is going to reduce. So because it has been moved through another chamber, and then it will be moved to still another chamber. And the pressure will continue decreasing until it reaches 200. So the other chamber, which the gaseous mixture is taken through, is the heat exchanger. So from the purifier, we take it to compressor to compress it to 500 atmospheres. Then from the compressor, we take it to the heat exchanger. At the heat exchanger, this mixture is heated to a temperature of 500 degrees Celsius. And this hot mixture is then taken to catalytic chamber. So in the catalytic chamber, this is where the reaction between nitrogen and hydrogen occurs. Why? It is because all the conditions required for this reaction to occur, they are present in the catalytic chamber. So in the catalytic chamber, we have optimum conditions for maximum production of ammonia. Which are these optimum conditions? You can see from the chamber we have a catalyst, which is ion. So one of the optimum conditions is ion catalyst. The second one is temperature of 500 degrees Celsius. And the third one is pressure of 200 atmospheres. So we have 3 optimum conditions that are required for maximum yield of ammonia, which are these: ion catalyst, temperature of 500 degrees Celsius, and pressure of 200 atmospheres. So in the catalytic chamber, nitrogen will combine with hydrogen and form ammonia. Now, the products now from the catalytic chamber are taken back to the heat exchanger. Because they are hot, they are taken back to the heat exchanger to cool them. And the heat which is absorbed from this hot mixture, that is the hot product, it is used in heating the incoming reactants. So which are these products from the catalytic chamber? We have 10% liquid ammonia. So this means of all the ammonia that is formed, only 10% of it is liquid, as the rest is in gaseous state. Then we also have unreacted nitrogen and hydrogen. So they are hot. They are taken to the heat exchanger to cool them, and so that that heat can heat that hot mixture can heat the incoming reactant, you see. So from the heat exchanger, the mixture is taken to the condenser. At the condenser, all the ammonia will now turn into a liquid. So ammonia gas will be collected in liquid form. So that is the gas we were preparing. So it is going to be collected in liquid form. So ammonia gas is collected from the condenser in liquid state. Then remember we had an reacted nitrogen and hydrogen. So they are going to be taken back to the compressor so that we can increase their pressure again and take them to the heat exchanger, then the catalytic chamber to react further. So that is the whole process of that is the whole process of preparation of ammonia. So how what is needed of you to know? Number one, the raw materials, you can see them. They are nitrogen and hydrogen. How many volumes of a nitrogen react with a hydrogen? So only one volume of nitrogen combined with 3 volumes of hydrogen. So when you see a gas whose volume is just, when you look at their reacting volume ratios, and you see one gas is 1 volume or 1 mole, then that gas must be nitrogen. The other one, which is hydrogen, must be 3 moles or 3 volumes. So when you look at those ratios, we'll see one gas is 3 times more than the other. Then the one that is 3 times more, that is hydrogen. So these raw materials, we have said, they are taken to the purifier to remove the impurities that could otherwise poison the catalyst, then taken to the compressor to increase the pressure to 500 atmospheres, then the heat exchanger to heat that gaseous mixture to 500 degrees Celsius, then to the catalytic chamber where the reaction occurs between nitrogen and hydrogen. Then in this catalytic chamber, we have said we have 3 conditions that are necessary for that reaction to occur. For the maximum production of ammonia, the first condition is temperature of 500 degrees Celsius. The second one is pressure of 200 atmospheres. Then the third one is ion catalyst. The gaseous mixture from the catalytic chamber, we have taken it to the heat exchanger to cool it, then to the condenser to convert the ammonia into liquid, and then the unreacted nitrogen and hydrogen, they were taken back to the compressor so that they can continue following the, going to the heat exchanger and then the catalytic chamber for that reaction. So that is the whole process, the Haber process. So we have said the optimum conditions that are necessary during this process are 3. One is pressure of 200 atmospheres. 2, temperature of 500 degrees Celsius. And the third one, the catalyst, which is ion catalyst. Now, we have said in the catalytic chamber, that is where reaction occurs, and that is where we have all these optimum conditions. So in that catalytic chamber, the nitrogen and hydrogen reacts. So how do they react? So the reaction between nitrogen and hydrogen at 500 atmospheres, 500 degrees Celsius, and the presence of finely divided ion catalyst is usually this one. 1 mole of nitrogen combines with 3 moles of hydrogen to form 2 moles of ammonia. So we had seen before that the reaction between nitrogen and hydrogen is to form ammonia is usually a reversible reaction, but in the presence of these optimum conditions, the forward reaction is favored. In the presence of these 3 optimum conditions, the forward reaction is favored, and that's why here we are writing only the forward reaction, because we have used all the conditions necessary for the forward reaction to occur, which is now will lead to the maximum production of ammonia. So the other thing you usually need to know after learning these Haber processes are the uses of ammonia. And the first one is that ammonia can be used as a fertilizer. So fertilizers are substances that are used in crop production to make the crops to grow faster and to yield more. So these are the fertilizers, and the ammonia is one of them. So during crop production, you can produce crops like products like the cereals, fruits, and vegetables. All these they need fertilizers for them to do well. Then another thing is that ammonia can be used in manufacture of nitrogenous fertilizers like the ammonium nitrate. So these nitrogenous fertilizers, they are used in also in crop production in agriculture. Then another use of this ammonia is that it can be used as a refrigerant in ships and warehouses. So this ammonia will be used to preserve perishable goods in ships and warehouses. Warehouses are just store for goods. So these are ships that may be ferrying some goods. So ammonia can be used to store them, to cool them as a refrigerant, to prevent them from going bad. Another use of ammonia is that it can be used in softening of hard water. Hard water is water that cannot lather easily with soap. If you go to places where the water is containing calcium and magnesium ions in it, or soluble salts of calcium and magnesium, this water cannot lather with soap easily. So what do if you want to wash clothes with using the water? You can add ammonia to precipitate all the calcium, not the calcium but the magnesium ions. So if the water is containing magnesium ions, you can use ammonia to precipitate all the magnesium ions in that water and make it soft. So once you have done that, then the water becomes soft and it can easily lather with soap. So another use of ammonia is removing of grease stains. So if your clothes are stained with grease, then you can use ammonia to remove the stains. The other use is the manufacture of hydrogen. So hydrogen is used in rockets as fuel. So ammonia is used in the manufacture of hydrogen, which is used as rocket fuel. So in short, in summary, we have said the uses of ammonia include: can be used as a fertilizer, can be used to manufacture nitrogenous fertilizers, it can be used as a refrigerant, it can also be used in the softening of hard water and removal of greasy stains, and lastly, manufacture hydrogen. And that is the end of the Haber process. So let me give you some revision questions. The first one: name two gases used in the large-scale manufacture of ammonia. Name two gases used in large-scale manufacture of ammonia. The second one: during Haber process, 3 moles of gas A combine with 1 mole of gas B to form 2 moles of ammonia. Identify the sources of the gases A and B. Identify the sources of the gases A and B. The third question, 3A, name 2 impurities removed in the purifier during Haber process. Name to impurities that are removed in the purifier during the Haber process. Part B. Why is it necessary to remove these impurities? Question 4. State 3 conditions necessary for maximum yield of ammonia during Haber process. State 3 conditions necessary for the maximum yield of ammonia during Haber process. Question 5. Apart from fertilizers, state any 2 other uses of ammonia. Apart from fertilizers, state any 2 uses of ammonia. And the last question, state any 2 environmental problems associated with the use of inorganic fertilizers. Last question, state any 2 environmental problems associated with the use of inorganic fertilizers. So that is the end. Thank you for watching. The answers to those revision questions can be availed in the next video. So continue following. Thank you.